So this is section 5.4, which takes a closer look at titrations. We're going to actually start this lesson with a little bit of a warm-up, a little bit of a theoretical exercise. So the first section of this warm-up is asking what is the formula equation for each titration. Now remember that when we're doing a titration, we're looking at a neutralization reaction. So in the first titration, we're going to be looking at the reaction between sodium hydroxide and hydrochloric acid. In the second one, we're going to be looking at sodium hydroxide and acetic acid, so a little bit different, a weak acid this time. And then in the third titration, we're going to use our strong acid, hydrochloric acid, and a weak base, that's the ammonia. So there's our first neutralization reaction. You can see that we're making sodium chloride as our salt and water. There's the reaction between sodium hydroxide and acetic acid, and we're creating that sodium acetate ion and water. And then finally in the third titration, we're mixing our hydrochloric acid with the ammonia ion, and we're making ammonium chloride. So what salt solution exists in each reaction flask at the equivalence point? Now, that is the salt that's created by that acid and base neutralization. So in the first one, you can see that we made sodium chloride. In the second one, we made the sodium acetate. And then in the third one, we made ammonium chloride. Now, it's looking at the next step is to indicate whether you'd expect pH of each solution to be below, equal to, or above 7 and explain your decision. So with this one, what we're going to do is actually a hydrolysis reaction. We're going to split this into our spectator ions, or we're going to split it into ions, and then we're going to eliminate spectators. So you can see in the first titration, both the sodium and the chloride ions are both spectators. So they're going to cancel out, and we're going to expect a neutral pH. With the second titration, however, we get our sodium spectator, but we also get that acetate ion. And acetate is a base. It's a weak base. It'll go on to react with water to form acetic acid and hydroxide. In titration number 3, again, the ammonium is acting like an acid in this case. When we combine it with the water, we get ammonia and we get hydronium ion. So what we expect from the pH is that the first titration, we're going to have a neutral. It's going to be 7 because that salt doesn't undergo hydrolysis. They're both spectators. Titration number 2, we're going to expect that we have a base solution. We get base hydrolysis happening. And titration number 3, we're going to have a pH of less than 7 because it's going to undergo acid hydrolysis. So how does this affect our titrations? That's what we're going to be moving on to. So we're going to look at titration curves. That's the pH range and how our pH changes as we continue adding drops of an indicator solution. We're going to compare titration curves for strong acid, strong base titrations, strong acid, weak base, and weak acid, strong base titrations. We're going to explain how to choose an indicator for our titration. And then finally, we're going to look at finding the pH at the equivalence point. And the notes go a little bit into finding the pH of a weak acid, strong base, or a weak base, strong acid indicator. But we're just going to look at it for a strong acid, strong base solution because of a time constraint and being in a distance format. So first off, here is the titration curve for a strong acid, strong base titration. Now, if you take a look at the pH right at the beginning when we have a volume of 0 NaOH, this is the first place we're going to look at. So this is our acid that's in the Erlenmeyer flask before our standard base is added. In this case, the concentration of acid is equal to the concentration of hydronium because I have a strong acid here. And the pH is just going to be easy. It's going to be a negative log of the concentration of hydronium. So we can calculate those very quickly. The second point here is when we've started adding some sodium hydroxide. So we have excess acid. It's still an acidic solution, but it's not, we have neutralized some of it. So our concentration of hydronium here is going to be the number of moles of acid, subtract the number of moles of base because it's being neutralized and turned into water, divided by the total volume. The third point is a really important point. This is the equivalence point. This is where our indicator solution starts to change color. And this is where we would stop that titration if we want to figure out what the concentration of the acid was. So at the equivalence point, we have the concentration of hydronium equaling the concentration of hydroxide. And when we have a monoprotic acid and a monoprotic base, and a standard base, we have a pH of 7 here because it's in a 1-to-1 ratio. Finally, for number 4, we have base in excess. So the concentration of hydroxide here is the moles of base minus the moles of acid divided by the total volume. So in this case, we're doing our neutralization, but we have extra base. And our pH is going to be 14 minus the negative log of the concentration of hydroxide. And the reason for that is because we're converting it into an acid land term when we're looking at a base land concept by doing the negative log. So we're going to be calculating the POH and then taking it from 14. So there's some standard calculations that you can do with a titration curve with a strong acid, strong base. So here's an example of a problem with our strong acid, strong base. Calculate the pH of a solution produced in the reaction flask during a titration following the addition of 12.5 mils of 0.1 molar sodium hydroxide to 25 mils of 0.1 molar hydrochloric acid. So our first step here is we're going to find the moles of hydronium and the moles of hydroxide and figure out which one is in excess. So I'm just using my stoichiometry calculations here. I'm multiplying the molarity by the volume, and you can see from this calculation here that I have excess hydronium. So step 2 is to figure out how much excess hydronium there is. So we're going to find the molarity by dividing by the total volume. So I'm taking that acid minus the base and then dividing by the total volume. And that gives me an excess concentration of hydronium of 0.0333 moles per liter. Last step is to calculate the pH. So I'm just going to, I have hydronium here. If I take the negative log of that hydronium, I get the pH. And I've got 1.477. And I'm looking, I should actually have, I do have 3 sig figs because I'm counting after the decimal place for a pH value here. So there is my final answer. Here's another type question. It says determine the pH of a solution produced in the reaction flask when 25 mils of 0.1 molar sodium hydroxide has been added to 25 milliliters of 0.1 molar hydrochloric acid. So when we do our moles of hydronium and moles of hydroxide calculation, this time we find that both of them are equal. Neither acid nor base is in excess, so it completely neutralizes. Now in this particular solution, we have to be very careful because we don't actually have 0 moles per liter of hydronium or hydroxide. What we've done here is we've created a neutral solution. And neutral solutions have a pH of 7.00. So technically we have a concentration of hydronium of 1.0 times 10 to the negative 7. So we have to be a little bit careful with this question because it doesn't follow the exact same pattern, but we have to use our logic because we know that when we have a completely neutralized solution, our pH is 7. So what we have here is a generality that we can make. When we have a titration of a strong monoprotic acid and base, it will have an equivalence point at pH equals 7. Now the second thing that we're going to move on to is a weak acid, strong base. And you can see that the titration curve here looks a little bit different. We've got this buffering region in the middle. So we spoke about buffers in our last lesson, and buffers turn out to be really, really important in a acid-base titration when we have a weak acid and strong base, or strong acid, weak base. You'll also notice here that our equivalence point has moved up a little bit. So when we have a strong base, weak acid titration, the equivalence point is not 7, it's slightly higher than 7. So we're going to look at the reasons for this. So our first point is the same as a strong acid, strong base titration. This is the acid before the base is added. Now, because this is an acetic acid, it's a weak acid, we actually have to use an ice table to find the pH in this particular question. The second region here is in our buffering zone. So you can see that when we add acetic acid with sodium hydroxide, we actually create the salt of the conjugate base. So we're creating a buffer solution in here. And that is going to resist changes in pH. And that's why our curve looks a little bit different. Third point here is the equivalence point. So at this point, we have equal moles of acid and base. However, the pH is greater than 7 because of our base hydrolysis. So it takes the same volume of sodium hydroxide as it did for a strong acid, strong base titration, simply because of that hydrolysis and the buffering effect. Last step here is where we have base in excess. So the buffer doesn't last forever. It can be overcome and we can overthrow that buffering region there. But we do go back into base in excess at point number 4. So our kind of generality here is that a titration of a weak acid and strong base has an equivalence point at a pH greater than 7. Takes the same volume of base to reach that equivalence point as a strong acid, strong base titration. So you can see a comparison of them right there. Weak acid, we start with a higher pH. However, it takes more base. It takes the same amount of base to get it to that equivalence point. And the equivalence point has a pH greater than 7. Now, there's some questions in your notes. You can skip these questions at this point. They're an extension of the curriculum that I've done in past, but we don't need any further complications to this semester, so just skip these ones. Okay, last two scenarios here. This one is a strong acid, strong base titration. This one's the same as a strong base, strong acid titration. It's just going in the opposite direction. So we're starting with the base this time. We're adding acid. You can see the equivalence point, because it's strong acid, strong base, is still, again, at 7. Here's the titration of a weak base and strong acid. So again, you can see this buffering region. So at point number 1 here, we have only weak base. And again, we're going to need to use our ice tables. When we find the concentration of hydroxide, we're going to have a baseland thing. So when we take the negative log of that, that gives us our POH. If we want to find pH, we have to subtract that from 14. In the buffering region here, what we're creating when we mix hydrochloric acid with the ammonia is that we're going to get ammonium chloride. So we have the salt of the conjugate acid. This is going to resist that change in pH. At the equivalence point of a weak base strong acid titration, you'll notice the equivalence point is less than 7. So equal moles of acid and base, but we have that acid hydrolysis. And then finally, this last point, we have acid in excess. And that acid in excess takes us down the rest of the curve. Now, choosing an indicator is the last part of this particular lesson, trying to figure out which indicator we use. What you want to do is use an indicator that signals when we reach that stoichiometric point. So with the strong acid, strong base titration, we're trying to find an indicator that changes pH around pH of 7. Usually we use phenolphthalein. Phenolphthalein actually isn't the best indicator to use for strong acid, strong base titration because it changes color between 8.2 and 10. However, it's really, really easy to see the change between colorless and that bright pink. So that's why we use phenolphthalein. But if we were looking for something that actually changes color around a pH of 7, phenol red would actually be a really good indicator to use. It's just more difficult to see the change from yellow to red. So we're really trying to find a pH at the transition point of the indicator that is the same as that stoichiometric point that we're expecting. So here's our last example question. It says, which indicator would be suitable for the following titrations? In this first titration, you can see we have a weak acid and strong base titration curve. So that's the WASB, weak acid, strong base titration curve. At the equivalence point, we have a pH of 9. So if we go back to our chart, we are trying to find something that changes pH at around 9. And in this particular case, phenolphthalein is a great choice. Thymol blue is another one that changes color right in there. So there's two good choices for that particular titration. In the next one here, you can see that we have it must be a strong acid, weak base titration because we have a pH at the equivalence point of 5. So what we're looking for is an indicator that changes color around a pH of 5. And bromothymol green changes color, methyl red also changes color at that point. So those are suitable indicators for those following titrations. So I hope this lesson helps you understand a little bit more about titrations and some of the little technicalities that come with them. Please email me or ask for a Zoom conference or something if you have any questions about titrations, and thanks for watching.